Thanks for the privilege and welcome again to our next clips as we continue with our subtopics in elementary set theory. Now today we will talk about power sets. Power sets. Now what are power sets? These are a collection of all possible subsets. They are a collection of all possible subsets of a set. They are a collection of all possible subsets of a set. And I know this we have done in our previous class. Now, let's consider a set, say A, where its elements are 1, 2, and 3. Let's consider another set, say B, where its collection is A and B. Let's consider another one, say C, where its collection is just A. And lastly, let's look at another collection where its set is a null set. There is no element in it. Now, the power set of this set, we are saying that they are the possible sub-collections, possible collections of subsets of this set. Possible collection of subsets of this set. And mind you, power sets is denoted as P. So if we are referring to as power set of A, this we write as this. Now, if we are to determine the power sets of this, we are saying the possible subset of this set A, and this includes, we have said for the collection of subsets, the null set is a subset of every set, and the set itself is a subset of itself. So we are going to start with that of the null set. Say phi is a subset of this set, is a subset of every set, and this one here is a subset, this set here is a subset of this set. 2, 3, we have 1, 2, we have 1, 3. All these are subsets of this set. And we have 2, 3. And lastly, the set itself, which is 1, 2, 3. All these are subsets of this. This and this is an improper subset because you can see that this is a subset of this and this is also a subset of this. Now, whereas all these ones are proper subsets of this set. So the collection, let me enclose this. The collection of these subsets is what we refer to as power sets. The collection of these subsets is what we refer to as the power set. And in this, we can also talk about the cardinality of the power set of A. The cardinality. And we said the cardinality is simply the size of that set. So, and the size, which is the number of elements in that set. So in this case, this set is an element of this set. So, and we have them in terms of another set. In another way, we also call this type of presentation set of a set. Set of a set. Set of sets. Set of sets. Also, sometimes we say families of sets. All these we call them either set of sets or we say families of sets. And the cardinality, as we know, is the cardinality of A, of the power set of A, is how many elements are there in it. 1, 2, 3, 4, 5, 6, 7, and 8. You can see that the cardinality is 8. In like manner, we can also determine the power set of B, where we said is the possible subset of possible collection of subsets of this set A. So we say the power set of B is equal to the possible collection of subsets of that B. And we said the phi is a subset of every set. So phi is here. Phi is here. We have A there. A is there. We have another set B. So all these, if you can see, they are all subsets of this set. And we have A, comma B, which is the set itself, because we said every set is a subset of itself. And we can also talk about the cardinality of the power set of B, which we have as this. And it simply means the number of elements in that set, and they are 1, 2, 3, 4. The cardinality is 4. In like manner, we can also do that of the power set of C. Power set of C, where we have said is the possible collection of all subsets of that set. First of all, we determine the null set, which is a subset of every set, which is a subset of every set. And the set itself, in this case, we just have one element, the set itself. So these are the possible collection of that set. And if we want to talk about the cardinality of the power set of C, the cardinality is just simply 2. And lastly, D. And D, we have it as a null set. So we can also talk about the cardinality, the power set of D. And it simply means the possible collection of all subsets of that set. Now, in this case, there is no element in it. And we have said that the null set is a subset of itself. And that is the same thing as the set. So here we just have phi. And if you're talking about the cardinality of the power set of D, the cardinality is 1. So this is all about power sets. Power sets, conclusively, power set is a collection of all possible subsets of that given set. The possible sub-collection of all the subsets of that set. Next, I want us to talk about disjoint sets. Disjoint sets. Now we have disjoint sets. Disjoint sets. Now we are saying that two sets, say A and B, are said to be disjoint if and only if they don't have anything in common. Two sets are said to be disjoint if they don't have anything in common. In other words, you can say if their point of intersection is 0, if their point of intersection is empty. Now let's consider a set, say E, where its elements are 1, 2, and 3. Let's consider another one, say F, where its elements are A and B. Now, if we are to consider if these two sets are disjoint, what do? It's simply to determine the intersection, which is E intersection F. Do they have anything in common? You can see that these are numerical numbers, whereas these are alphabets. So that set is 5. Nothing is there. Nothing is there. It's an empty set. So when you consider the intersection of two sets or three sets, and you find out that the resulting set is 5, then you know that those sets are called disjoint sets. They are called what? Disjoint sets. Two sets are said to be disjoint if and only if they don't have anything in common. Now let's consider another one, say P. Let's consider another set, say P, where P we have A, 2, and B. A, 2, and C. Now, you can also determine if F and P are disjoint sets, are F and P disjoint sets. You now see that their point of intersection, F intersection P, is they have something in common. There is a set element, we have this, and that's it. So you see that they have something in common. Being that they have something in common, you say they are not disjoint. They are not disjoint. Now let's consider if E and P are disjoint. Now in them, if you consider the intersection, you also see that one is here, one is not here, 2 is here, but 2 is here. So also in this one, you see that they have something in common. So if they have something in common, you know that they are not disjoint, because disjoint sets are sets that does not have anything in common. Their point of intersection is phi, is empty. Now, lastly, I want to quickly talk about the universal set. The universal set. The universal set. The universal set. Now, what is the universal set? The universal set is a set that is made up of the collection of all the elements from every other set. It's made up of a collection of all the elements from every other set. Or you can say the universal set is a collection of all the elements from the other set and other elements that are not also in it. Now, let me give an example to illustrate that. Let's consider two sets, say A, where its elements, let's consider these two sets A and B. Now, in these two, among these two, if we are to determine the universal set, I said it's a collection of all the elements. It's a collection of all the elements. And universal set we denote as this. It's a collection of all the elements. And we have been told that when collecting the elements, no single element should be repeated. Now in this case, for that of A, there are numerical numbers 1, 2, 3. Whereas for that of B is A and B. So it's a collection of all of them. So the universal set is simply 1, 2, 3, A and B. So you can now see that all these ones, all these smaller sets are subsets of the universal set, because the universal set comprises of all the elements from the other sets. Now, and we can also talk about the cardinality of the universal set, which is simply the size. The size of it, and we have it as 1, 2, 3, 4, 5. The cardinality of this universal set is 5. Now, we can also consider other sets, say D. Let's consider D, where D we have 2 and A. Now, if we are asked to determine the universal set in this case, you will now see that in D we have 2, and 2 is also here. In B we have A, and A is also here. So the collection will still be this one that we have presented, because we are not allowed to repeat any element. Now, the other case is given a universal set. Given a universal set, say 1, 2, natural numbers less than equal to 10. Now we have another set, say A, where its elements are 2, 4, and 6. Let's say we have another set, say B, where its elements are 1, 3, and 7. Now I am saying that the universal set here is a set, and now this A and B, you can see that all their elements are contained in this. They are all proper subsets of the universal set. Even B here is a proper subset of the universal set. But there are also some elements in the universal set that are not in these ones. So I said in the other definition, and I said universal set is a collection of all the elements from the other sets, from all the sets, including the ones that are in it. So the ones that are not in this one, that are in the universal set, in this case is 5 is there, 9 is there, 8 is there. So including those ones that are in this one, but not in A and B, all of them are made up the universal set. So conclusively, we can say, given two sets A and B, the universal set is a collection of all the elements in A and B, including the ones that are proposed to be in the universal set, like in this case. So the universal set is a collection of all these subsets, as we have illustrated earlier. And we can always talk about the cardinalities of the universal set, which is simply the size. Like in this one, the cardinality of the universal set of this one is 10. The answer is 10. Thank you, as we look forward to studying other topics in our next class.